Hi everyone, in this video we're going to start topic 6 and we're going to be talking about electromagnetic radiation, which oftentimes takes the form of light, and how it interacts with molecules. So we'll start by saying that light energy has no mass and is a wave. If you're wondering what light energy is, it's weightless and it comes as a wave. So let's explore that concept a little bit more. So light energy interacts with molecules. It interacts with our chemistry. So here's an example of how light actually interacts directly with molecules, a real life example of this. So in your eyeballs, you have these chemicals. You have vitamin A, or retinol, which gets converted to the cis-retinol molecule. So how we are able to see things in the environment in front of our eyes is by the conversion of this cis-retinol molecule. So this is light incoming here. And when light hits this retinol molecule, it alters it, it changes it, it makes it into a new structure. And so what happens here is that these chemicals, this retinol, is in the cones in your eyes. So there are rods and cones in your eyes. And when that change happens, what it does is it sends a signal to your brain that says light's been encountered. So here's the, this is the protein here that this trans retinol is in. So after it gets hit with light, it changes from cis-retinol to trans-retinol. And it's actually in your eyeball here. All right, cool. So on a smaller scale, here's kind of what's going on inside of each of these rods. So this is the rod here. This is a protein. And what we're saying is the light energy is incoming. And when it hits this cis-retinol, it turns it into trans-retinol. And what that does is it causes this protein cascade here with the G protein, which attaches to this PLC, which attaches to this PIP, and all kinds of other stuff. And it goes over here and opens an ion channel. And ion channels, what they do is they let things like calcium ions, calcium, magnesium go through, magnesium 2+. And when these calcium and magnesium go through, what they do is they produce a charge, because the positive is moving from one side to the other. And that gives us our electrical signal, which then goes to our brain and says, hey, this rod over here has intercepted light. So how do we see different colors? So we have different types of rods and cones in our eyeballs, and each one of those detects a different color of light. So if you'll notice here, we have a blue receptor, a green, and a red. And you can see that inside here is our cis-retinol. And so this is in each of these here. They're bonded to different locations on the rod, which indicates what kind of receptor it is. So here the blue is bound here and here, the green is bound here and here, and the red is bound here, here, and here. So it's still cis-retinol in each of these proteins, but they're bound to the protein slightly differently. And so it requires a different amount of energy to change its structure. So when blue light has a specific energy, it's got this wavelength, it hits the retinol, it's going to change its structure and send that electrical signal to the brain. Now when you get a wavelength that's green, your 534 is about where green is, it's going to change that structure, say, hey, we've encountered green light. Or red, say it's this wavelength here, it will change the structure, send a signal, say, hey, we've encountered red light. So your brain gets a signal depending on what wavelength it encounters, because different wavelengths turn on different rods. Okay, so here we have a high energy molecule, or high energy radiation, sorry, and this is low energy light, or red light. We're going to learn about this in just a minute, how to know which one's high energy and which one's low energy. Okay, so here's an overall. Your blue, green, and red Opsin enzymes, these are your enzymes or proteins right here. Enzymes, they're the same thing. Don't be confused by that. Enzymes are proteins. Not all proteins are enzymes, but for your purposes, this is not a biochemistry class, so we're okay. And different wavelengths convert your cis-retinol here inside your molecules to trans-retinol. So cis-retinol is in all of them, and it's converted for each of them. Okay. So that's a real-life example of how electromagnetic radiation changes molecules and why it matters to us. So let's take a look at the more basic principles of electromagnetic radiation, what it is, and how it's composed. So think about light coming off the sun. The light that comes off the sun is electromagnetic radiation. It's a form of it. And each light wave that comes off of a source has a specific length between its waves. This is what we call a wavelength. So if we think of the light coming off the sun as a wave, we see the distance between the peaks is our wavelength. And the waves occur at a certain frequency, i.e. how often they repeat, and they travel at the speed of light to Earth. So they have a certain speed, just like a car, except this is a fixed speed of light that all light travels at. So we can represent this relationship using this equation here. We can say that speed of light is fixed. All light travels at this speed. That's 3.0 times 10 to the 8 meters per second. And this speed of light is related to the wavelength of light that is around. So it's equivalent to our wavelength times our frequency. Frequency means how often the waves are forming. So we see these different units here. Wavelength is a distance. So it's how far it is in between your between your waves of the light wave. It can be a lot of different numbers. So its base unit is meters, but it can go from any, it's got a lot of different distances. So it can be really, really small. We could have something in nanometers, or we could have something really big, like meters, or even bigger, maybe even kilometers. Maybe a wave is a whole kilometer in wavelength. That is possible. A lot of times when we're dealing with light, we'll be talking about nanometers. It's not always true, but be on the lookout this chapter. You're going to see a lot of things in nanometers. Frequency is in inverse centimeters, or hertz. I'm going to show you what that is. Okay, so let's delve into frequency here. We've learned what wavelength is. We understand what speed is, which is our c value. So let's check out our wavelength, which we represent with this Greek letter nu here. So we have two different ways that we can determine frequency. One of these is the amount of times something happens over a certain time period. So here we can say this is an example of a wave, and you can see that this distance here is 1 second on this graph. So i.e. this wave happens 1, 2, 3, 4 times per second. So that's a frequency. It happens 4 times in 1 second. Okay, so this is our unit for frequency. Inverse seconds. 1 over seconds. So this happens 4 times per second. We give this a frequency of 4 inverse seconds. So the unit that we use to represent that is called hertz. We abbreviate that as Hz. And hertz is equivalent to 1 over seconds. They're the same thing. So make sure you don't get those confused. Another way that we represent frequency, oftentimes when we're talking about light, is when we talk about how many times the light wave occurs per distance. So we had said per time. So let's look at a distance instead. Let's say this is a centimeter. And so over 1 centimeter, we have this wave occurring a certain amount of times. Okay, so we have a unit of inverse centimeters. So this wave happens 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 times per centimeter over this distance. So that would be 14 centimeters, inverse centimeters. So this is the same as 1 over centimeters. Please don't confuse those units. So we can represent our frequency in either inverse centimeters or inverse seconds. Either one is acceptable. You're going to be doing a lot of unit conversion in this chapter, so be very careful to use the one that is appropriate based on whatever equation you're using whenever you're doing calculations. Okay. All right. Okay, let's take a look at another property of light. So I had told you that in the rods in your eyes, you have different types of proteins or enzymes that convert different wavelengths, right? So we've got one specific to blue, one specific to green, one specific to red. And the reason that these activate is because each of the red, green, blue wavelengths have a different energy, because we have to break chemical bonds. In order to do that, we have to put in some kind of energy in order to do that. So our waves of light have an energy, and they're related to each other using this equation here. So the energy and wavelength of a light are inversely proportional, meaning that as wavelength goes up, energy goes down, and vice versa. If energy goes up, wavelength goes down, because you can see here that our wavelength is in the denominator and this is in the numerator. So as one increases, the other one is going to decrease. Okay, so let's take a look down here at an example using this principle. So use this inverse relationship here between wavelength. So use this inverse relationship here between wavelength and energy in order to determine which wave has higher energy. Remember, the definition of wavelength is the distance in between two peaks. So let's take a look at how to solve this one. So first we need to figure out which one has a higher wavelength or a larger wavelength. So we can see here, this is one distance here versus, say, this distance here. This is bigger, right? This one's further apart, bigger, smaller. So if we want to know which one has higher energy, the higher energy is going to relate to our wavelength. So if we have a smaller wavelength, we have a higher energy. So that means that this one is higher energy. And this one is lower energy. So this is an important equation you're going to be using a lot. The H and the C in this equation are constants. So this H here is what we call Planck's constant. Planck's constant. This is a value that you will be provided on the exam because it's a really big number and you're going to need it for a lot of calculations. This is a constant. It never changes. Whenever you convert wavelength to energy or energy into wavelength, you will need this value. Same with speed of light. It is also a constant, and we represent that by using the variable, or by using this letter here, C. So this is speed of light. Something else that I want to point out is that energy here, our energy is in a unit called joules. We haven't encountered joules yet. This is our first time seeing this. This is a new unit. And it's how we describe energy. So you'll be seeing that in your calculations. If you look here, Planck's constant is joules times seconds. So we need our Planck's constant in here so that we can convert joules to other units such as seconds and other things such as meters. Let's take a look at the electromagnetic spectrum here. So you can see these different relationships between energy, frequency, and wavelength as we have different types of electromagnetic waves. So here are some different types of waves that you actually have probably encountered. So we have radio waves, like the radios that we listen to. These are really large waves. So if you look here, this is your wavelength This is kind of the wavelengths, and you can see that these are a whole meter long. So radio waves are actually like this long. Then we get into microwaves, the thing coming from your microwave oven that you cook stuff in. And we've got a smaller wavelength here. So now we're in nanometers, 10 to the 6 nanometers. And then we get into infrared, so infrared light, IR light. That's our 10 to the 3rd nanometers. Okay, so we're getting smaller and smaller and smaller here. This is visible light. So these are the colors we can see with our eyes that our rods and cones pick up in our eyes. Then we have UV lights. So this is the stuff that's responsible for tanning when you go out and it burns your skin. That's your UV light. Then we get higher energy, such as like X-rays. When you get X-rayed at the doctor, they use this type of electromagnetic energy. And then we have gamma rays, which is radiation, what we typically call radiation. Technically, these are all radiation, but this is what we think about when we think about harmful radiation. We're going to learn why. So you can see the wavelength difference here. Radio waves really big. Things that have high energy, like gamma rays, X-rays, UV lights, have very short wavelengths, but very high energy. That's what makes them damaging. And these are not damaging because they have a low energy. We also have our relationship down here between frequency and wavelength and energy. So remember, frequency is how often something happens over a specific distance or specific time. If we look here, this is going to have a lower frequency than these up here. They're going to have a much higher frequency in that same distance. And so this is high frequency, low frequency, and this is how they're related to wavelength and energy. And we know that relationship between these equations. So we have C equals lambda nu, wavelength times frequency, and then we have our energy equals hc over lambda, which is our wavelength. So these are two very important equations you're going to be using a lot. So I had described some of the sources of these different types of radiation. Here's a couple more just for you to be able to see where these things are coming from. Your radio spectrum, these are things that are considered non-ionizing or typically non-harmful. So things like your radio waves, the signal from your mobile phone, your mobile router. So if you have internet in your home, microwave oven, that sort of thing. And then we have things that are on the spectrum of non-ionizing to ionizing. They're kind of in between. So we have IR radiation, UV radiation. So you get that from a lot of different sources. Here's some of them. And then we have our harmful ionizing radiation. This is an important term, non-ionizing and ionizing. And this comes from things like medical x-rays, medical PET scans, CT scans, and then we also have things just like in outer space or cosmic radiation, or the UV light that's blocked, or the UV light that comes down to Earth that burns your skin, right? That's harmful ionizing radiation. Okay. All right, so let's go ahead and put the stuff that we learned into practice here and doing some conversions. Okay, so the first thing here that I'd like you to answer is this one. These are two separate questions, so just answer the first one first. This is our microwave here, and our microwave oven operates at a frequency of 2.45 megahertz, so 2.54 megahertz. And I'm going to ask you to find out what wavelength of radiation that the microwave outputs based on this information. You can use this equation here. I've given you some of the useful values and units. Pay very close attention to units here. Make sure things cancel, okay? And remember that hertz is in inverse seconds, 1 over seconds. You'll also need to convert this megahertz to hertz in order to be able to answer this question. So go ahead and give your best shot at answering number 1. All right, let's take a look at how to solve this problem. So we want to first start with our megahertz and get that into hertz. So 2.54 2.45 megahertz. We're going to need to convert that into regular hertz. We know that mega is 10 to the 6. So there is 1 times 10 to the 6 hertz for every 1 megahertz. So if you multiply this out, we get 2.45 times 10 to the 6 hertz. Remember that hertz is in inverse seconds, so this is also the same thing as saying it's 1/seconds. Let's go ahead and put this into our equation now and solve for wavelength. So we're going to solve for this lambda variable here. So speed of light is 3 times 10 to the 8 meters per second. If you'll notice, I'm putting in my units here. This is really important. I always like to keep track of units, make sure that I've converted everything properly, because you wouldn't want to say plug the megahertz straight into this equation and try to solve, because they wouldn't cancel, the seconds wouldn't cancel. So be very careful when you're working these. So we're going to solve for lambda, and we're going to put in this value from here. So 2.45 times 10 to the 6. Because if you didn't convert to megahertz here, you'd just be putting in 2.45 and you get a very wrong answer. That's why it's important to use our units, so 1/seconds. All right, so let's solve. We have 3 times 10 to the 8 meters over seconds, and we're going to divide that by 2.45 times 10 to the 6 inverse seconds to get to lambda. All right. We're going to see that our seconds cancel out here and that we end up with meters as our answer. So what we find when we do this math is that lambda is equal to 122 meters. We know this is meters, not nanometers, because of us keeping track of our units and knowing that that is where that is coming from. All right, so let's give number 2 a shot. So see if you can calculate the energy of this wave that we determined from question 1. What is the energy of this wave given our calculations for our wavelength at 122 meters? You're going to need Planck's constant, which is 6.63 times 10 to the minus 34 joules times seconds. That's the unit on Planck's constant. So give this a shot. Let's take a look at how to solve this problem. So we're solving for energy, and we want to input Planck's constant times our speed of light first. So we're going to go ahead and get that on top here. 6.63 times 10 to the minus 34 joules times seconds. And we're going to multiply that by our speed of light, 3 times 10 to the 8. Oh, I'm running out of room. Meters per second. And that's all going to be over our lambda value. So we're going to put that over 122 meters. And so now you can solve for energy by plugging this into your calculator. One way you can check that your number is right is by checking your units. This is a foolproof way to make sure that you're right. So you can look here, seconds cancels with seconds because this is in the numerator, denominator, they go away. We have meters on the top here, meters on the bottom, they cancel, they're going away. We're left with joules. We know we're right when we put this in our calculator because our unit that we're left with is joules, and we know that energy should be in joules. So we've done this calculation correctly. The number that we end up with when we do this calculation is that our energy is equal to 1.63 times 10 to the minus 27 joules. That's a very small number. For this chapter, you're going to be using a lot of really small numbers, a lot of really big numbers. You're going to need to use this scientific notation a lot.